All right. Good morning, everyone. Welcome to lecture 13, I think. Is that right? Let me just double check yeah, lecture 13. That's a good number. All right. Welcome to lecture 13. Here's the Slido. Here's another QR code. We check these surveys, so please do this if you haven't done so already. We're seeing okay turnout, but more turnout would be better, as we've discussed in sampling. Let's get out of the way. Take your picture. All right. So today, I'm going to try to do a little bit of a recap from lecture 12 because we did a lot of linear algebra and that can be confusing. And we're going to build on the linear algebra, so it's important you understand what's going on. And then today, we will start gradient descent. One of the coolest, hottest algorithms of 2024. Billions of dollars are being spent on gradient descent every week, every month, I don't know. It's the thing that everyone's computing. So we're going to learn it today, hopefully. All right, so this is actually goals from yesterday's today, so we're on Tuesday. We were going through the process of ordinary least squares. Professional audio settings, we'll turn that off now. If there's issues on Zoom, I guess leave a note and hopefully we'll try to fix it. Okay, so we were going through ordinary least squares, and we had this model we had set up last time. We're looking at multiple dimensions now. So we have data, which is not just one column of data, but a couple columns. In this setup, we said there were p columns. We'll talk more about our p's in a moment. And then our model was a constant, theta 0, plus all these extra theta coefficients for each of our features. And then we went into this long but important regression, I don't know, into linear algebra. And we're going to use that some more today, so let's go through it once more. So we had our data matrix X. It's a matrix. It's also a data frame for us, but it's a matrix because now it's going to be all numbers in our matrix X, or a data frame X. We call this our covariate matrix. This is our features. But we're trying to predict Y. So in our label, in our data, we have this extra column Y. Those are things we're trying to predict. We're trying to predict star ratings, income, something. It's a quantitative continuous field, but we're trying to predict it. So we're doing regression. We built this model up here, which we can now write using linear algebra right here. What is going on? X, that's my covariate matrix. Looks like this. By the way, I'm bad at linear algebra. I will make mistakes during lecture. To make my life easier, I always draw rectangles. So if you're having trouble with linear algebra, draw some rectangles. So we got this rectangle. It's got n rows and records of data. P plus 1 columns. Why does it have P plus 1 columns? We have this intercept. And then we go 1, 2, up to P coefficients. I'll show you in a second. We added an extra ones here. I'm going to rename this in a moment. But let's just say we have our matrix P plus 1 columns. And we multiply that by this vector. It's a skinny vector. This length is 1. And this length is what? P plus 1. Oh man, I'm going to mess this up. Okay. What happens when I take this row here, or maybe this row here, and I multiply by this, is I'm going to take this row, multiply by that, and that's going to give me this equation up here. Right? So this is just a nice linear algebra shorthand, this thing right here, for this equation up here, this equation right here. Getting messy. Okay. And again, this is my data. This is my data frame with my P plus 1 columns, and then my one extra column of things I'm trying to predict. And here's the linear algebra way to write my prediction. I call Y hat my prediction. That's my guess for what Y is. I have Y, but in the future I'm going to get another X for which I don't have a Y. I want to make guesses for it. This Y will not necessarily be the same as this Y because I'm making a prediction. I'm going along that line, right? My data may not be on that line. This is what I actually observe. Okay, it's my response to my label, sometimes written as, let's clear this up once more, as what I observe. Okay. Observed, make it past tense. All right, so I said I'm going to struggle with these P's and P plus 1. So I'm going to do something to make life easier for us on the slides. I'm going to say that this theta 0 is hard to keep track of. So I'm going to start with theta 1. So I go from 1 to P. So I'm going to have just P columns. And if I wanted a theta 0, I'll just add an extra ones column at the beginning here. See what that does? put an extra ones column, theta 1 becomes my new theta 0, right? It's a cute trick. We did this in previous lectures. I'm going to use that throughout this lecture. So instead of having p plus 1 everywhere, I'm going to have just p. So just p. Just p. And I can add my columns of 1s to encode the intercept if I want it. And this is desire. If I don't have to have an intercept, I can say, you know what? I don't want this. I'm just going to start with my actual data. I can add an extra column of 1s. It's a modeling choice I make. All right. Questions with the setup? Questions about the setup for this model? Who's feeling, I get it? Who's feeling like not responding? Yeah, very good. Okay. People aren't getting it or not responding and not voting. Awkward. Let's keep going. Let's keep going. Okay, one more thing here. That was our setup. We chose a model. And by the way, this formula right here, choose a model, choose a loss, optimize it, and evaluate it. That is the formula, the process for all the modeling you will do. Even advanced neural networks follow this exact same 4-step recipe. Step 2 was choose our loss. This is measuring how good our predictions are relative to our data. What's a loss we all love? The squared loss. Why do we like it so much? It's measuring difference. Square difference is nice. It's nice. And what does a square look like? A parabola. We'll talk more about why we like parabolas later. But this is a loss we use. Simple linear regression use squared loss. We also sometimes call this least squares regression because we're trying to minimize the square of our error. Okay, so this was the error on all my data. I averaged it, so this is the mean squared error, the mean of the square of the errors. And then we did linear algebra again. We wrote this. Why does that work? Okay, let's break it down. Y minus y hat, that's just the difference between these two vectors. This one here. Oop. I wish I had an eraser. That's the difference between this vector here and this vector here. My predictions. Difference. What's the difference between two vectors? A vector. How big is that vector? What's the dimensions? What's the dimension of this resulting vector? We'll call it R. N by 1. Same dimension as this. This is 1 by n. 1 by n. Okay. This here says take the sum of the squares of the value. This is the, actually, says take the square root of the sum of the values. So the like R1 squared plus R2 squared. This is the Euclidean norm. This right here is our standard Pythagorean theorem, right? But generalized to many dimensions. How many dimensions is this? N. Interesting, right? So this vector here is an n-dimensional vector. This difference vector R is tall and skinny like that. Okay? And I'm going to take the sum of the squares of these things, and I'll take the square root, and then guess what I'll do? I'll immediately square it again. So what is that? The square of the square root is the thing. So this right here is the sum of the squares, also known as that, right? Everyone with me so far? We got the model, we got the loss. There's questions on Zoom, and I'm not good at Zoom. So if there are questions on Zoom and I need to know it, or people let me know. I apologize. Zoom. Maybe ask the questions on Slido. Slido is a good place to check. Ask questions. Okay. So now we have our model. We have our loss. And then in last lecture, we derived this amazing equation. I'm not going to do that again. So go back and watch the last lecture for that derivation. But let's talk about this equation today. This is the normal equation. It's super cool. It's normal because it was about this geometric interpretation of something that was normal to the plane. Go see last lecture. But what does this look like? I draw rectangles. So let's walk through my rectangles. Let's talk about X transpose X. Here's my data matrix. Remember, down here's my data matrix. Here it is again, a little X. And I transposed it. What does that mean? Flipped it on its side. That's this matrix right here. What happens when I take these two matrices, zoop, zoop, and I multiply them? I draw rectangles, so I know that one side's going to look like that. One side's going to look like that. So I get a matrix that looks like this. What's the shape of this matrix? P by P. Let's talk about this for a minute. We have millions of records, and maybe 3 or 4 dimensions. These things are really tall and skinny, right? So I'm down to have just like 3 by 3 little matrix. That captures everything I need to know about my x's. It's kind of cool, right? Okay. Let's look at this side. X transpose Y. Here's our data again, flipped on its side. Where'd the ones go? I had ones here. If I had the ones, where would they be? Right here, right? There's my ones, right? I'm going to multiply and I have my other features here. I'm going to multiply each features times this y. That's kind of weird. That's what it says to do. I get this p by 1 thing, so p by 1. So we get this other little thing here. Bring it up a little bit. This is pretty cool, right? What is that? I have a matrix. It's called M because matrix M. There we go. And I have maybe another matrix A. And I have this thing theta. Theta is a vector, but it's a random variable. So I have sort of like, M times theta equals A. If this was just basic algebra, what would you do? You'd divide by M. Divide by M, and you go, well, theta equals A divided by M. Oh, that's what we did right here. We did the linear algebra version of that, which is we take the inverse of this matrix right here. And we solved for theta. So if you bought that this was true, this was true, this is a hat, meaning this is our best estimate for the mean squared error, then that would imply that this other crazy thing is true. The theta hat is just this. So we know how to solve the normal equation to get a model. This is our model. Amazing. Questions? This is fast. This is big stuff. This is a basic building block of a lot of things. So you can use this same piece of math here to win the Netflix challenge for $1 million. Yeah. Great question. Is this always true? Maybe there are conditions I need on this X. And that is the next set of slides. So don't steal it from me. Before I do that, I want to talk about P and D. I will confess I am a computer scientist. I do not know why people use P. But my statistician friends refer to things as parameters, so they use P dimensions. I will say D dimensions occasionally, forgive me. Okay? When you look at textbooks, they will alternate between P or D, depending on what field they come from. So P dimensions, D dimensions, P parameters, D parameters. Bit of notation. And to the earlier question, we're generally going to have situations where N is much bigger than P. That's an important property, which we'll come back to when we talk about, does this actually work? Under what conditions can this be done? All right, in fact, it's right here. At least one solution exists to this problem. Actually, I want to jump ahead. I'll come back to the formality of it. Let's go back to this question of when I can solve this. And we'll start with a simpler question of when is this unique? What does it mean to be unique? Let's talk about that. We had this really simple model a while ago where we said, what's a good estimate for y if I just had to pick one number? I don't care what the features are. The income is theta 0 for all people. If I choose the mean squared error loss, the mean is that number. So just take the mean of your y's and say that's theta 0. Call it a day. This is always going to work, and it's always unique. That's nice. How about the median? Constant model again. Mean absolute error. So I want the mean absolute error for this model. Now the answer is the median. If I have odd data, the median is well defined. It's unique. If I have even data, I have to fix it. It's not quite unique. I can make unique by always returning the middle, the average of the two. Simple linear model here. It's the baby version of what we've been doing. A little constant term, one slope term, mean squared error. We derived theta 0 as this. We can always compute theta 0. Why can we do that? Because y bar, the mean of y, good to go. X bar, the mean of x, good to go. Oh, hold on, we got theta 1. This is a bit of an issue here. Let's talk about theta 1. Theta 1 is r times something here. And this maybe clues us into a problem. If there's no variability in x, what is this? This is 0. What's something divided by 0? It's not a number. We don't know. Undefined. So we need a non-constant x. We need variability in x for this to be unique. Right? For this to be defined. Does that mean I can't compute a line? What does this look like if I have no variability in x? What might that data look like? Let's draw some data. My little axes. Here's my y. Here's my x. No variability in x could look like doop, 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 doop. Fit that with a line. Well, okay, the line that goes up and down, we can't do that line. Slope infinity, not defined, sorry. But you know what? This line's pretty good. There are lines. Just, if I try to write it like this, I cannot. So there is a solution. I can pick many solutions. Remember, I'm finding the best solution. The best solution for mean squared error is the line that goes like this. That I can't define using this notation. Right? Okay. So now, for this box, what do you think? Unique. Any guesses to what conditions might make this all work out? Who thinks they know the answer to this? All right. Who's taken linear algebra classes before? Correlated. Okay. Good. Good. Let's talk about it. You guys see this? I wrote over the negative one. You see this? What does this need? What are we thinking when we see the inverse of a matrix? We might have some problems, right? Let's talk about it. This is unique. We can find the answer to this. You can solve this thing here. You can solve the system of equations if our covariant matrix is full column rank. I believe I'm about to try to do a proof. Okay, let's talk about that for a second. There may be many solutions if it's not full column rank. So there's always a valid value for this, but whether or not it truly minimizes a thing, and it is the unique one that minimizes it, depends on the conditions on X. So you can have multiple good lines, potentially. So let's talk about those conditions. So here's an informal sketch of a proof. The least squares estimate, theta hat, that we've been defining, is unique if and only if X is full column rank. Proof sketch. Here we go. So we need to solve this system of equations. Remember, this is essentially M times, if you like your old algebra textbook, oh, I can't do that. Okay, theta. We'll use theta as our variable equals A. It's a system of linear equations, and we can solve that. We can invert X transpose X. Okay. And it's invertible if and only if X transpose X is full rank. The rank of number of linearly independent columns, the rank of it is the number of linearly independent columns of that matrix, with the matrix X transpose X. Okay. This actually applies to X as well. So we need X to have P full rank. So let's draw that picture real quickly. I draw my rectangles. There's my X matrix. I need this to be full rank. I need all these columns to be linearly independent. Okay. Can you think to yourself, when might this not be true? In practice, when you get real data and there's noise and stuff and your matrix looks nice and tall and skinny like this, generally going to be true. It's good news. Oh, terrible rectangle. Generally going to be true. But you're going to do feature engineering and do things that add extra columns. Sometimes those columns might be functions of existing columns. That could be a problem. If you say, you know what, I think I'm going to take this column here and multiply it by 10 and add a new column that's 10 times that column. Good feature. It's linearly a function of this other column. Now we broke this rule. Okay. All right, so when is not unique? Oh, I gave it away. Bummer. Okay, well, here's another reason why you might have a problem. When your data looks like this, fat matrices where you have P is way bigger than N. You're saying I want to fit some data to this thing where I have very little data and lots of features. There's many ways you could fit that data. It's underdetermined. When does this happen in life? When might you see this situation? Biologists get this all the time. They have like 10 rats and they have all this DNA information. All these like factors that they measured in their 10 rats. They got a problem. Stay tuned. We have a solution for this too. We can resolve this situation. All right, so that's one way this happens. Computer vision, you got few images. Each image is many, many, many pixels. Right? How do I fit models to that? But typically, in this class, we're going to have N much bigger than P. So that's not usually a problem. The more likely problem is you invent new columns. And in the next lecture, we'll talk about how inventing columns can be useful. Adding columns that are not linear combinations of your existing columns is a good way to improve your model. But adding columns that are linear combinations ensures that X is no longer full rank. All right, so that's the formal mathematics. We will solve these problems by using regularization, which you'll hear about later. And the numeric tools that we use today will actually ultimately pick just one of these potentially good solutions. So in practice, this is not so catastrophic, but you need to understand the underlying mathematics. All right, questions up to this point? Well, I'm behind. Okay. Our Slido questions looking a lot. That's good. We'll call good not a whole lot. All right, great. So now we're going to do a demo. And today we're going to be predicting the bill length of a penguin. Nope, the bill depth. This is an exciting number. The bill depth of a penguin, I assume based on its body mass and the flipper length. I don't know why they're related, but let's do some modeling. And we'll actually work through using the normal equations in code. Okay, do demo quickly or already behind. Oy, that is true. Okay. Here we go. So I'm going to pull in one of these kind of toy data sets in Seaborn, penguins data. I'm going to study these Adelaide penguins. I'm dropping all the things with missing values. Should be worried about it, but for today's purposes, who cares? So we're going to just focus on a subset of these penguins. And let's do some analysis. All right, so I'm going to look at just these columns. This is my data matrix. And this is my Y. I'm trying to predict bill depth. And these are going to be my X columns right here, flipper length and body mass. So that's my data frame. Here's my model. I decided to add an intercept term. So I want an intercept plus theta 1 times flipper length, and then theta 2 times body mass. Okay. How many dimensions is this model? What is P for my covariate matrix? Correct. It is 3. How many parameters are in this model? 1, 2, 3. Got it? Okay. Some math that we've drawn on the slides. We won't do that. Let's make our matrices. So I'm going to take, this is kind of cool. I'm going to take the 2 columns, the flipper length and the body mass, and make that X. And I'm going to add a bias term. Let's look at X. Here's my matrix. 3 columns, 1, 2, 3, and I've made theta 3, or I guess theta 2 if you count from 0, the ones. Doesn't matter where I put this, I could put it over here. One of my terms is going to be multiplied by 1, so I'm going to have this extra theta that's just a constant. Build depth, it's my y's, another column matrix, or series in this case. And look how easy it is to do this math in Python. So I say, this is matrix inverse, this is matrix multiply, this is X transpose. So I do X transpose times X inverse, zoop, right there, times X transpose times Y. Boom. Solved a system of linear equations, figured out the best model. Easy if you just copy the equation. Very good. You shouldn't do this. Okay, so I just did a matrix inverse and then a multiply, which is jargon for saying solve a system of linear equations. I could just ask the linear algebra library to solve the system of equations. But this is my matrix M, and here's the thing I'm trying to solve equal to the column vector A. Why would I want to do this? Computer scientists have thought long and hard about how to make this more efficient than this, because they end up solving one of these and then doing a multiply up here when they could just solve directly. So if you want something a little bit more stable, but doesn't look exactly like the equations here, this does the same thing. Computes the same answer. Which one should you use? Turns out neither. In today's lecture, I'll tell you another way to solve these things using software packages, which are just more robust in general. But it is important you understand the underlying linear algebra. So how do we make predictions? We've got this theta using normal equations. It's my little column vector of thetas, 3 by 1 for my 3 dimensions, 3 parameters. I can predict the x value for all the penguins in my data by just multiplying x times theta. How easy is that? And I went and stored it in the build depth, predicted build depth mm, also known as y hat. Well, let's see how we did. Here's our prediction. Here's what we measured. Prediction, measured. Pretty good, huh? How would we measure if it's any good? Probably want to look at the loss, right? Oh, but I don't have time. We're behind. Okay. As an exercise, compute this mean, the root mean squared error of this with this. Okay. You can do it in Python, 1 line. Turn to slides. All right, and now we're ready to start today's lecture. 30 plus minutes behind schedule. Today we're going to talk about scikit-learn and gradient descent. Who's heard of scikit-learn? Awesome. Why? I don't know. Okay, who's heard of gradient descent? Even more awesome. Everyone's going to know about gradient descent. It's the hottest new thing, as I said. All right. Scikit-learn is the package we'll actually use for most of our modeling in this class, and probably in your early careers as data scientists, you will use this package a lot. So we'll talk about how to use it to fit linear models, and then we'll talk about the mathematics behind it with gradient descent. Man, that was a long walk to get to here. So we did all that work in geometry, and now we're going to use algorithms. So scikit-learn is a package you've already heard of, many of you. It's a library for creating and training models. Who's heard of these other packages? XGBoost, interesting. Okay, this is a package for decision trees we won't cover in this class. PyTorch, another great machine learning library for AI, for neural networks. TensorFlow, very cool. This is a Google package, again, not in this class. And then what's this last one? Hugging Face, which is an emoji, also for AI. So all of these packages here are out of scope for this class, very much in scope for your life. They're AI packages. The cool thing is, actually this one too, the cool thing is they all decided that they'd probably like to be kind of like scikit-learn, so they have a lot of the same functionality, same interfaces. So we teach you scikit-learn, which does the basics. I use it in my research all the time to analyze my data. And hopefully in knowing this, you'll learn a little about these things too. At the end of today's lecture, I have some links on tutorials. With an hour of your time, you can become a pseudo expert on this as well. So if after this class you want to learn more, you can do that on your own. All right, so here's the recipe for scikit-learn. It is this easy, and that is a problem. So step one, pick your model. So I'm using linear models, linear regression. That creates an instance of a model. In scikit-learn, a model is kind of really equal to our model plus a loss. So most of the models have a built-in loss. So when I choose linear regression, that's the linear model with the least squares loss. Okay. So now I have a model with the loss. Step three in our system, fit it to the data. Scikit-learn, you say my model.fit. Here's my x, the covariates, and here's the thing I want you to predict. Scikit-learn is like check. It then does all the optimization for you. And this is one of the maybe 50 models it supports. So just change your model, run the same code, you get another prediction, another model. Okay. How do you make a prediction? I've just fit my model. Inside of this object are all the thetas. If I want to make a prediction, I say predict my model. Once it's fit, it uses all these thetas on some new data, which could be my original data, to make predictions. Very easy. For some of the models, the linear ones in particular, I might want those coefficients. You can access it by saying my model.coef. It returns those parameters we just estimated. And it's nice, it makes it intercept its own little separate parameter. Really easy to use. And that's a problem because you can use crazy models and get yourself in trouble. So focus on linear regression for now, because we kind of understand that one. Oh, demo. Exciting. All right. Using scikit-learn for multiple linear regression. So it's this. Uh-oh. Why can I not click? There we go. So I'm going to import my linear regression package, a linear regression object class. I'm going to make a linear regression model. This is how you create an instance of an object. So I say linear regression. There's a bunch of arguments I could set here. I could turn off the intercept, turn it on. I can use parallel computing, but we're not going to do that today. You get a model. It's got this really cool interface, kind of shows you what's going on. Linear regression, simple little model. It's orange, it means I haven't fit it to anything yet. So I can't make predictions because there's no parameters. Step two, fit. It's pretty easy. So I take my data frame, I say X is going to be this. This is my covariates. My label wants to be the build depth. Why am I using two brackets here? Because I have a list of columns. Multiple linear regression, right? Boom. Done. Make a prediction. Can plug in a random, this was build depth in millimeters and weight in grams, I think. So I plugged in some numbers I made up, and it's going to predict, fin length, I think, and weight. I'm going to predict build depth. Go. Build depth is 18. Kind of cool. It gave me this warning. That's really annoying. Why is it yelling at me? This is actually really a neat feature in scikit-learn. When I fit a model giving it a data frame, it really wants to make sure that I give the column names to my data when I pass it in. Why is that a problem? I've made this mistake. I changed the order of my columns and I pass it in. Linear models don't care. They're matrices. So just, you put your columns out of order, you'll get crazy answers. Scikit-learn goes, hey, you didn't name your columns. I'm going to run it for you anyways, but you maybe should think about it because your columns could be out of order. If I just pass in my data frame, which has named columns, I run it, it makes predictions. These are my predictions. They're exactly the same as the ones I got from my linear algebra, but I didn't have to do any matrix stuff. And if I flip my column order, what's going to happen? What will happen? Make a typo. What will happen? Gives me an error. I was hoping it would run, but it tells me it cannot run. Why? Because I messed up my column order. So it's sensitive to the names. Safety feature. Make predictions using data frames. Really easy. Make your model, fit your model, make a prediction. That would have been a much faster way to give the last 2 lectures. But it's important you understand the math behind this. So what's the intercept going to be? Coefficient? How many parameters do I have? 1, 2, 3, right? 3-parameter model, same as before. And let's compare it to our other thing. 11.0299. Yep, that was my intercept term. The last column, because I added all the ones at the very end of my covariate matrix, was 11. And this is for my solving linear algebra before. And then did I get these terms the same? Yep. 0.9828 and 1477, so on. Okay. Questions? All right, let's do some fun stuff. We can visualize the fit. What will this look like when I try to plot this? Is it going to be a line? Is it going to be a plane? How many dimensions was my original data before I had that intercept term? 2. I had 2 features, right? And I'm trying to predict a third thing. How many dimensions is this thing going to look? 3. But there's another dimension, which is my parameter for my intercept, which is going to affect the picture. When I visualize this, what will I see? Go, 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 go. No, don't zoom out. Okay, here you go. This is how you visualize this data. So we have the body mass of the penguin, the flipper length of the penguin, and I'm trying to predict the bill depth. These blue dots are my data, and that plane is my model. Did I do a good job? Not bad, right? I added if I did not have an intercept term, what would be true about this plane? It goes to the origin. Very good. Why would it go to the origin? Because when I say that body mass is 0, flipper length is 0, 0 times theta 1 plus 0 times theta 2, and there's no intercept term is 0. So the thing I can predict when I have body mass 0, flipper length 0, is that bill depth has to be 0. But I add an intercept term, so now bill depth can be that intercept term when there's 0, 0. So it's no longer going to the origin. And I didn't plot the origin, but you could extend this plot to see that this plane does not pass the origin. In fact, where does it go through at the origin? (11). We know that the plane at the origin is going to be 11, not 0. Because we say when everything else is 0, the intercept term is 11. All right, hopefully you're understanding this. Analyze performance. Oh, I took it away from you. Okay, so let's compute the mean squared error. So I'm going to import metrics because it's too hard to write 20 characters of code. But anyways, there's a mean squared error metrics built into scikit-learn. Take the mean squared error of my bill depth and my scikit-learn predictions, and I get this number. What units is this in? Mean squared error. Well, this is in millimeters, I think. Bill depth is in millimeters. Scikit-learn predictions are in millimeters. Mean squared error is therefore in millimeters squared. I have no clue what that means. What should I do? What units is that in? Millimeters. So on average, I'm about 1 millimeter off in my predictions. Pretty good model. I'm pretty happy with that. Bonus. I should never do bonuses. Let's do it anyways. Okay. What if I want to use a crazy model? We haven't taught this yet. Let's use a decision tree regressor. Who knows what that does? We can create an instance of it and we can fit it, right? Boom. Fit a model. Can make some predictions. I'm going to just say predict. Just change my model from linear to tree model that I just fit right here. So crazy new model. Mean squared error. Oh, I don't like those units. Square root. Oh, 0.2. So much better. See, you can change your model and you can have a much better fit. That's what scikit-learn makes very easy. What do you think this looks like? Nice. Such a better plane, right? Some of you are laughing and you should be laughing because this is a bad idea. This is why scikit-learn is a little bit dangerous. You could just change your model, get better results, and go, look, I'm clever. In the next few lectures, you'll find out why this could be a terrible idea. But that's cool. So scikit-learn does make it easy for you to try any model and get really good results. You don't have to understand any of the algorithms, any of the math, just fit and predict. Okay. Exciting. Come on, how do I scroll? Okay, return to lecture. All right, so here's a recap, which I won't go through. We did that in great detail in the lecture, or in the demo. For those on Zoom, you can just jump to this if you need to. All right, so how do these software packages fit models in general? How do they do it? So they use numerical optimization, and that optimization is often some variation of this gradient descent algorithm, which is the focus of today's lecture. So up to this point, we've been using calculus-based approaches or geometric techniques to solve our problems. Calculus is amazing, and we'll continue to use it, but we were algebraically solving for the 0 points. We had a curve like this, and we're like, oh, I want to find the bottom of this. I take the derivative. What's the derivative of this? It looks kind of like this. That's unfortunate. Okay, well, here we go. We can fix this. Let's call this the 0 point of my axes. So, okay, and so where it goes through 0 is the bottom of this thing. Right, so we're using this calculus idea that if I can compute the derivative, and where the derivative passes through the 0, that's where the minimum of these things are. Right? That was what we did up to this point, but that's not going to work in practice for really big problems, and when these things no longer look like that, right? So we can't do that. We also tried a geometric interpretation. Instantly, you can use calculus, matrix calculus, to solve the normal equations, but we also found a geometric way to do that. And that is only going to work for linear models and mean squared error loss. It's kind of a bummer. We spent a whole lecture on a thing that only works in one very special case. Wouldn't it be cool if there were just a general thing that works in all situations? You're in luck. Gradient descent. Kind of works in all situations. So it's designed for more complex models, and it's a new optimization technique. Let's do it. Big idea. We're going to use an iterative algorithm to numerically compute the minimum. No more solving stuff. We will use calculus. We're not going to solve any equations. We're just going to take steps in the right direction. Okay. Let's just build this in. All right. So I'm going to work through a simple example in today's lecture, not a model building thing, just a simple minimization problem to build an intuition. They're going to apply the algorithm to a very simple model, one which we already know how to solve analytically. And I'm going to describe how this generalizes to any model. Okay. And remember, our goal in this class, at least, is to find the parameters that minimize the model's loss. We want to find the best parameters for our model to make it fit our data the best we can. So let's do it. Minimizing a 1D arbitrary function. Here's my function. Where are the minimum of this function? Humans are great at this. You go, I see it. The minimum is right here. Done. Piece of cake. Okay, but this one's easy. It's in one dimension. You can do it. Higher dimensions can be harder. The minimum of the function is right there. Just be really clear here. The minimum point is there. The value I want is this point on this axis, right? This is my, if this was my loss problem, this would be the loss dimension. And this would be a 1-parameter model. So this would be theta, my 1 parameter. And this is my crazy loss. And the lowest point on this loss is right here. And so I'd say I like this theta. I might be okay at this theta too. It's not so bad, right? You go right here. Ooh, sorry, right here. But this is the best one. Everyone see that? Okay, so that's our goal. Try guessing and then using numeric oh yes, let's do that. Okay, so let's do a quick demo. I was up late, so I have to write notes to myself. All right, so here's our crazy function, which which we're calling our arbitrary function. I'm having so much trouble with the slide. did some silly stuff. Past that, okay. All right, so here's our function. Let's plot it. Or plot our function. By the way, I do all of my plots in Plotly. In this class, we're focusing on Matplotlib, but if you want to learn other visualization tools, in the lectures, I'll use Plotly for stuff because I can kind of mouse over and see what things look like. All right, let's do the naive thing, which actually works in a lot of situations. Let's just guess. So I'm going to make some guesses. So I'm going to try a couple guesses. The simple minimize just evaluates the functions at those locations and chooses the argmin, the thing that minimizes my function at those spots. Does that look like? So I took these guesses and it said this guess is my best guess. Good job. Right? Trying and guessing, like trying things out and testing a model is actually not a terrible strategy. And advanced techniques will do this and then use clever heuristics to figure out if I figured these guesses look like that, maybe I'll improve my next guess a little bit more. So this is a technique. But in high dimensions and in complex problems, this is not going to perform well. I really want to use more information about my function to find the lowest point. There's another tool that we used in Data 8. This tool actually uses this guessing strategy, but as it builds these guesses, it estimates the derivative of the surface, uses those derivative estimates to improve its answer. So it starts with an initial guess and a function. This is a SciPy optimized package, which is pretty powerful. Inside of it, it uses gradient descent and a whole bunch of other algorithms. I say minimize my function f, that was this function here, this blue line, and start the guess of x equals 3.5. Where's that? 3.5, like right here. That's my initial guess. Boom. Super fast. It says the x value is 2.393. Is that good? Uh-oh. Went this way. Let's make our guess a little bigger, like 7. Oh, 5.32. That's over here. Interesting. So it depends on where I start my guess. Why? So I'm going to try to walk down some hills. It's using something like what we'll cover in lecture. If I start over here, it goes, that's the best choice. If I start over here, it goes, this is a better choice. Right? Not a great way to optimize, but you have an idea of a basic package for solving these kinds of problems. Okay, so to minimize, return to lecture. So let's invent gradient descent. How would you find the bottom of a complex surface? You're walking around campus and you want to get to the bottom of campus, but you can't see anything around you. All you can see is where you're standing. What would you do? If you were a skier, what would you do? Yeah. Oh, you guys are getting fancy. Newton's method. Who walks around doing Newton's method? I see the slope goes this way. I'll just walk downhill, right? We're doing simple stuff. Newton's method is actually a very sophisticated optimization technique that second order does more than we'll do here. This is going to be a really simple algorithm. But it turns out this is what we actually use when we have billion-dollar problems to solve. Okay, let's find the minimum. So we're starting here. And in the real world, you don't get to see the blue line. All you get to do is see the little slope around you. How is the shape of the land that you're standing on? So what's this slope? This is the change. So it's a change in this direction, went up, or a change in this direction. Is this slope positive or negative? First of all, is the slope, is it a number, a vector? What is it? Slope of this line is a number. It's a number. And it seems to be, it's the ratio of the change in, okay, well, it's the change in y over the change in x at that point, right? It's a positive number. So I've depicted that slope as saying go this way. So if I'm standing on a hill, which way is the slope point? This is a 1D hill. So the slope says go right to go up. First big insight. Also common source of bugs when implementing this algorithm is I don't want to go in the direction of the slope. I want to go in the opposite direction of the slope. I'm going downhill. So the slope says go this way. So I say, great, I'm going that way. going downhill. That's the algorithm. Figure out the slope, and then what? Take a step. How far? Take a step. Maybe we can start with just go however large the slope was. Really steep, take a big step. Not so steep, take a smaller step. Right? So this is the basis for all the innovation that happens in AI today. This simple idea, if I'm standing on a curved thing and I can figure out the slope, go the opposite direction. So I'm going to walk this way. Yeah, I'm in the parameter. I'm just a parameter, so my theta is right here. This is my initial guess, and it says, let's go that way. This is my new guess, right here. What should I do again? I give it away. Compute the slope again. Slope says go right. I go negative slope. I go left. Go left. So where am I going to go? I'm going to go here. What do I do? I took a bigger step. So I went from here over to here. That was convenient. I'm down here. Now which way should I go? What's the slope? Slope is 0. Why is the slope 0? Draw our tangent line. What's the slope of that line? 0. So which way should I go? 0. I don't know which way to go. I'm at the bottom. So now we have a stopping condition. If we get to the 0, we're done. Right? Okay. What if I start out over here? What is the slope here? Draw that tangent line. Which way does the slope say to go for, what direction is the slope? Is it negative or positive? Slope is saying go this way. Negative slope. Which way should I go? The opposite direction. The negative of the slope, which is now positive, takes me there. All right, so depending on where I am on this curve, it's going to tell me which way to go. So how can we use this? Slide up. Write down gradient descent. What's the algorithm? While you're writing this down, I will take a 2-minute stretch break since we are an hour in. So I will see everyone at, we'll call it 12:05. Stretch. 46 people. Somebody's definitely writing Newton's method, huh? All right, 310. Come on. Let's see what people got. I think you keep going. Well, no, that's just the answer. You can't write gradient descent. You got to write down the equation. People. What is gradient descent? Gradient descent. I mean, it's true, but it's not helpful. Yeah, it could be that this Wordle is doing silly stuff and breaking up your answers, but. All right. 4, 2, 1. Okay, let's keep going. People got it? I've been told that people are confused about my P versus P plus 1 situation. How are we feeling about P versus P plus 1? Who's still confused about P versus P plus 1? Okay. I'm sorry. All right, I'm not going to try to fix this right now. Post on Ed. Maybe the punchline here is that I don't want to think about the intercept term, so I'm just going to assume that my matrix, my covariates, has an all ones column. And I'm going to say there are p parameters. And my covariate table has p dimensions, not p minus 1 dimensions, and there's this extra parameter outside. So I just want, everything is just p. There's p. Intercept is cooked into my features. All right, that's all I'm going to say. So here's our equation that you were supposed to write or make up on the previous slide. I have some guess for my best value so far. And I compute the slope of my function at that guess. And then the all-important negative. I subtract. I go in the opposite direction of the slope. You could say it is plus the negative slope, if you like. Questions? Yeah. Yeah, could I multiply the slope by some learning rate? Stop reading ahead in lecture. Yes, you could, and you will, but not yet. You have to discover how this is a bad idea first. All right, so my equation abstractly is next guess equals last guess plus negative slope at last guess. That's the procedure. And then some of you pointed out we might want to put a little bit of a coefficient right here. We'll come back to that in a little bit. Yeah. Oh, good. So could I find the other minima? Well, it might be. Every time I'm going to start the guess, I'm going to make another guess. In like big AI things, we'll make trillions of guesses before we get to the bottom. So it could take a long time. Lots of little guesses, and often will take really small steps. Because we don't want to overshoot that minima. So you make small steps each time. And how big of a step? As someone pointed out, we might want to put a little bit of a thing here. We'll come back to that in a moment. Oh, demo. Excellent. Okay. These just work. It does. Okay. So the gradient of this is this. How did I do that? How did I do that? I don't have this equation anywhere else. All right, let's just try to, we'll sketch it out. I'm going to take the gradient, the derivative of this thing with respect to x. Derivative of x to the fourth is x to the third times 4. Derivative of 15 times x to the third is 45, or 3 times 15 times x squared. You're going to have to know calculus in this class. There are two things you really want to make sure you're comfortable with. Taking derivatives of things like exponents and products, and the chain rule, which I don't know if we have on slide form, but I'm going to just write it down so everyone has it. Way behind. What just happened? Oh, slide up. Okay. Chain rule. Do I have a slide that's blank? Yeah, let's try to write this down real quickly here. So chain rule. I want to compute the derivative with respect to x. Make this bigger. The derivative with respect to x of f of g of x. How do I do that? Really, really useful. First, I take the derivative with respect to u of f of u. And then I take this whole thing, and I'm going to evaluate that at u equals x. Then what do? Take the derivative, I multiply this times the derivative with respect to x of g of x. The chain rule. Useful because I have things of things like squares, my loss function, right? You have sometimes the loss of y, and so this is a function of my y hat, which secretly is a function of theta, right? And I want to take the derivative of this thing with respect to theta. Very useful technique, the chain rule. If you're confused about the chain rule, go to office hours, ask someone. It's really useful, not so bad, and critical to doing all the stuff that we'll do with gradients in this class. All right. Now I'm going to regret that because we're behind. All right, so I have my gradient. I derived this in LaTeX here. I've just implemented this exact equation down below. 1/10 times all these things right here. They made no mistakes. So now I can plot the derivative function of my blue line on the same plot. And you'll notice right here where this derivative function passes through 0 are interesting points on the blue line. They are the minima, the maxima, and the minima. They're inflection points of the blue line. Okay? But we're not solving this today, right? We're not doing analytic solutions of this line. We just need the gradient, the derivative, to tell us which way to go. So this is the actual code. Here's a point. There's the negative slope of that point. And I calculated this using my derivative function from above. So I take x, and my arrow goes in the x minus grad f direction, and I put the arrow at the position of f of x, so at this point on the line. It's my arrow. It's my derivative. Which way do I go? That direction. So we can now write this algorithm really simply. A take one step algorithm has a guess, takes a derivative, and it says my new guess is equal to my old guess minus the derivative. Turn my new guess. I can run this 10 steps starting at a guess of 4. And these are my guesses, the sequence of guesses for x. They are the sequence of guesses for x that's trying to minimize that blue line. But let's draw a picture, see what that looks like. Plot steps. Whoop, there we go. Here's my algorithm. Zoom in. So I guessed here, I took a step, guessed, that's my next guess. I took another step, a little bit steeper, bigger step. Now it'll get interesting. Okay, so as I go, jump over here. I go, nope, jump back over here. Nope, jump back over here. See a problem? Keep taking steps, and I get to the bottom of the hill. I go, jump over the other side of the valley. Oh, I should go back this way, take another step. I keep stepping over the bottom. How would we fix this? People need front. Don't answer my question. How would we fix this? It takes smaller steps. That would help, right? So maybe I could scale my step. That's my problem. So the solution, which I thought I do in the slides, is I'm going to add this extra alpha term. This is called a learning rate for those in the machine learning world. It's going to allow me to pick a number less than 1, and maybe I'll even shrink it as I go. So I take smaller and smaller steps so I don't overstep the bottom of the hill, the minimum. All right. Take one step now with alpha. My previous guess minus alpha times the derivative. I should pick a small alpha. Let's pick 0.3. Run it again. Zoom in. Zoom in again. Oh, zoomed in too far. Getting there. So close. It just keeps getting smaller and smaller. And it gets there. Why is my blue line not where my red dots are? Plotting error. There's no data here. This blue line isn't precise enough. To draw the blue line, I just sampled points. These red dots are exactly where the data is, where the curve is. Okay. So this is really good guess for the minimum. All right, questions at this point? Yeah. Is your alpha always between 0 and 1? Interesting question. Generally, it's not greater than 1 because you don't want to take too large of a step. It's usually a smaller number. And in some algorithms, we'll use something called learning rate decay, which is what it sounds like. You make the learning rate get smaller as you take steps. If you take 1,000 steps, make the learning rate a little bit smaller. Take a few more 1,000 steps, learning rate gets smaller. Why is this more efficient than just solving this with calculus? Great question. It's not. For this problem, I should just do the calculus. Well, for this picture, yeah, I could do the calculus. In general, you can't do the calculus. I don't know if I can solve this analytically. In general, you won't be able to solve these things analytically. Real world losses, real world problems have no analytic solution in many cases. And the advanced AI problems don't even have a unique solution. There are many, 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 many trillions of solutions that are local minima. Yeah. What if I started over here? Right here. Well, that would be unfortunate. I'd be stuck. If you started a minima, or if you started a maxima right here, you're stuck. Don't know which way to go. Would it be nice if I had some stochasticity, some randomness to help me? That's the end of this lecture, or perhaps the beginning of next lecture. We'll see. All right, so we are not here. We are here. Where's the zoom out button? Oh, there you go. Home. Okay, so we did it. Let's return to slides. All right, so we did our demo. Oh, let's clear this slide. So that was chain rule. Everyone remember it? Screen grab. Okay, it's gone. Let's talk about the actual algorithm. So we built a new algorithm, which is almost identical to the old algorithm, except we brought in alpha. Alpha is a number between, maybe don't do that, between, let's don't make it 0, that's a bad choice, 0 and 1. Okay, that's my algorithm. Pick a small alpha. Who picks alpha? You, the scientist. And do you tune your alpha? Yes, you do. Are there whole armies of techniques and people working on picking alpha? Yes, there are. A lot of AI research is about, what should I do with alpha? Okay. So that's kind of annoying, but this is the algorithm. That's the basic process. We didn't change much. When do we stop updating this thing? When do we stop? When is T big enough? Often after a fixed number of updates. When you are too tired. When you said, I've waited 30 minutes for the answer to my thing, 10,000 updates will be enough for me. If you're meta training the next super AI model, maybe 1 trillion updates is good enough. Right? Or it doesn't change much. Perhaps the gradient is 0. Does the gradient ever get to be 0? Does slope ever get to 0? In practice, no, but it gets really close. At some point, you're like, that slope is so flat, I'm not going to move anymore because I'm moving so slowly anyways. Yeah, so these are my 2 reasons to stop. Convergence, big question, out of scope for this class. When the algorithm settles on a solution and stops updating significantly or at all. So yes, you need to know what generally means to converge. Does this thing converge in general? Under complicated conditions, which I'll talk about in a moment. I think I already did this demo. I might have run ahead. Let me just double check. Oh, no, I didn't. Okay. Here's the full version of this algorithm. Let's just briefly highlight it. So we have my gradient descent. Oh, come on. Something is wrong with my Jupyter environment. Sorry about that. All right, here's my algorithm. Let's walk through it. Gradient descent takes a gradient, an initial guess, an alpha, and an n, which is the number of steps I want to take. I should have probably made that t. Oh well. Let's make it t. T. I'm going to do t steps. Okay. There's my algorithm. I start with my initial guess as my list of guesses. In this algorithm, I'm going to return all my guesses so I can plot it. And I take my current guess, and I say my current guess is my old current guess minus alpha times the gradient, evaluate the current guess. And then keep that in my list of guesses. Okay? Can run it. Can see it run. This is plotting that trajectory. If I start out over here, I get stuck here. And if I start out over here, I get stuck here. All right, so where I start, that initial guess does matter. Somewhat annoying. All right, let's keep going. So there are multiple minima. Where I start affects my answer. We might want to know what situations will there be one answer? And ideally, will it actually converge? A little bit out of scope for this class is this concept of convexity, but we're going to give you some basic definition that you'll actually work through in the upcoming assignments. So a convex function has this formal definition, which is saying that if I take any 2 points, here and here, and I interpolate between them, this is the line between those 2 points, it's this line, that is above the function everywhere between those 2 points. So this line is above this function here. So this is convex. This line goes above that line, so this is not convex. Okay. The intuition for convexity. Convexity is things where it's like a bowl. There's a clearly defined bottom, right? Give you one picture that might be a little confusing. How about this one? My function looks like this. Is that convex? Pay close attention to this thing here. It's okay to be equals. So I can take these 2 points here, and this line are on top of each other. It's still convex. Does not have a unique minima. So any of these things would be a good minimum. I think we're like right here, maybe it's right here. But it is convex. Okay. Oh no. So the nice thing is that any local minima of one of these things is a global minimum. So if I have a convex thing and I run this algorithm and I find a minima, I'm good. I cannot do, it is the minima. It is a minima. There's no better minima. It might be equivalent minima, but nothing better. The function in our demo is non-convex. Mean squared error is convex. It's even strongly convex. So it's a really nice error function because it's got a nice minima. It's a popular choice for this reason, because it's easy to optimize. Gradient descent, this new algorithm, is only guaranteed to converge given enough iterations and approximate step size and some conditions for convex functions. Otherwise, it could jump all around. Now, in life, again, a lot of the interesting stuff going on today is not convex. But in this lecture and in this class, we are generally going to focus on things that are convex, because that makes these numeric techniques really robust. And it is true that gradient descent is applied very commonly in non-convex settings, incredibly non-convex settings. All right, so now let's look at a 1D model. And I think we'll get to finish this, and then we'll start stochastic gradient next lecture. All right, so here's my loss for my 1D model, my parameter theta. We've already defined this. So I'm defining R, my loss, as this average loss over my data. Remember, this theta, this y hat here, is really implicitly a function of theta, right? So my model, my predictions, depend on my choice of theta. You can see why the chain rule might be important. What does this look like right here? Do I have it on the slide? No, I don't. So I have a nice parabola. What kind of loss would give me this? Squared loss, right? Squared loss, x squared looks like zoop. So this is a squared loss, and I'm trying to find the minimum. Remember, if I plot my loss surface, the parameter here is theta. It's my theta axis, and I want the value of theta that's at the bottom of this loss. Any point on this curve is a different guess for my model, but I want this one. It's the best one. Or maybe I want, sorry, this one right there. Okay. No, go away. All right. So now I can take that gradient descent algorithm and put it in terms of my parameters. So my next parameter guess is my previous parameter guess times the gradient to my loss. Again, here is where I'm going to want to use this chain rule, right? I think we're actually going to do the derivation. Let's try to do it. And next slide. Okay, we'll use some chain rule. So this is my model right here. So it's how many parameters? 1. Just a slope term, no intercept. Let's take the derivative with respect to theta. How do I do that? So I'll take the derivative slides through here, it slides through here. Now I start working there. So I'll say the derivative, my loss equals 1 over n 1 to n of the derivative with respect to theta. It's terrible theta of yi minus theta 1 times xi squared. Chain rule. See this thing right out here? My g, or my f here, is f of u equals u squared. And my g of theta is equal to yi minus theta 1 times xi. You guys see that? All right, so let's do the chain rule. So first I take the derivative of this thing. What's the derivative of this thing here? So, oh no, all right. Go fast. 1 over n. We're okay. Sum I equals 1 to n of, I got to bring this 2 down from the u, so I have 2 times yi minus theta 1 xi. Just did this part here of my chain rule. Now I got to do this part times the derivative of this whole thing. What's the derivative of this thing with respect to theta 1? Minus, so it's times a minus xi. Did I do it right? Hopefully. I think I'm on the next slide. Oh, okay. I did it right. Here's the answer. My derivative. So that, let's go back. So this 2, I'm going to bring it out over here. This minus sign I'll also bring out over here. And I get the negative 2, and the xi remains. There's my equation. There's my derivative using the chain rule. My update function for my gradient is I just plug this thing in right here, and I get this guy. Easy. Plug and chug. We can do it. We want to do it. Yeah, let's do it. And then next lecture, we're going to do the higher dimension stuff and stochastic gradient. And we just a tad bit behind. Half a lecture. Oh my. Okay. So my 1D model. Okay, and I think I'm trying to predict the bill. All right, so here's my loss surface. And for this model, I'm actually going to try to predict the tip from the total bill. And remember, every point on this axis here is a model for me. This curve here is the error I get from that model. Here's the gradient, and we derive this in the slide as the mean of 2 times this thing times x, and got the negative there too. Okay. My y hat was this theta 1 times x from before. So I can run the gradient descent algorithm we implemented earlier today for the random arbitrary function. I'm going to pick a negative 0.5 and a small learning rate. I'm run 100 steps, so I don't want to overshoot the answer. And here's what I get. Solves the problem. Okay, so taking small steps gets us to the answer in our 1D case. And we return to lecture. We recap. All right, so in the next lecture, we're going to do something crazy. We're going to push this to much higher dimensions. We're going to talk about the gradient as not just a slope, but as this vector in which direction we move. And at the end of what should have been this lecture, we'll introduce stochastic gradient descent, where we will use randomness to make these things work on really large data sets in massive dimensions. See you all on Tuesday.